So it's a pleasure to have here Shounak talking about typical basis for cosmological correlators from CAT.
So let me begin by thanking the organizers for this opportunity. This short talk will be based on this paper with Andrzej Pokraka, which appeared on Archive last week. So the central objects of interest in this talk will be these so-called wave function coefficients in a power law FRW cosmology. And as we've already learned from the fantastic talks on Tuesday by Austin and Claudia, these cosmological wave function coefficients are represented as certain twisted integrals. So the universal integrand making up these twisted integrals will be these differential n forms, which we call the FRW form, made out of shifted flat space wave function coefficients, which I denote by omega hat. Multiplying this FRW form is a multi-valued function u called the twist. And the twist is constituted out of the integration variables x raised to the parameter epsilon, which encodes information about the cosmology. So the first step is to compute omega hat. Now, apart from being described by Feynman rules, the flat space wave function coefficient omega hat admits a purely combinatorial description in terms of graph tubings. So to compute omega hat for any generic n-site L loop graph, we need to sum over all possible complete tubings. And by a complete tubing, I mean a maximal set of non-overlapping graph tubings. So given a graph tubing tau I, we associate a hyperplane polynomial, which is linear in the uppercase x's and linear in the y's. So for example, for the three-side graph I have here, so if we pick the yellow tube here, we see that it encloses the second vertex, which has a weight x2, and it intersects both the internal edges y1 and y2. So we assign to it a polynomial x2 plus y1 plus y2. And similarly, we can associate the various polynomials here depending on the various tubes involved in the complete tubing. Right, so to get to the cosmological wave function coefficient, we simply shift the hyperplane polynomials, which we obtained in the last slide. So we shift the uppercase x's with little x's, tack on the integration measure in the little x's, multiply it with the twist, and that gives us the twisted FRW integral. So for the three-site arrangement, I have 6 of these hyperplane polynomials BI. They correspond to two-dimensional planes in three-dimensional little x space. And in a more generic setting, each twisted FRW integral is associated to some hyperplane arrangement. So driven by the progress in deriving differential equations for Feynman integrals, there has been fantastic recent progress in deriving first-order differential equations for these wave function coefficients. Now, these twisted integrals form a finite dimensional vector space, and they are spanned by a basis of master integrals. And twisted cohomology predicts that the size of this vector space, or the number of independent master integrals, is given by the bounded regions defined by the divisors of the integrand, or so to say, the Euler characteristic of the hyperplane arrangement. But surprisingly, as Austin taught us on Tuesday, the universal rules of kinematic flow pick out a distinguished subset of master integrals, which is much lower than the Euler characteristic. So for going back to the three-site at tree level, as we will soon see, there are 25 bounded chambers, and hence we should naively associate 25 FRW forms. But we see that the physical DEQ system closes to a much lower number of 16. And this drastic simplification gets enormous at higher multiplicities and persists even at loop order. So the precise question we asked today is, are there any physiogeometric arguments that govern this characterization of the physical subspace of integrals onto which the DEQ closes? And the answer that I'm going to give over the next 10 minutes or so is that it is based on a combination of arguments based on unitarity cuts plus the geometry of the associated hyperplane arrangement. So as I've briefly alluded to, more formally, the FRW cohomology classifies all non-trivial differential forms on the manifold N, which is an n-dimensional complex space with the twisted lines and the hyperplane polynomials BI removed. However, our setting and our playground will be the dual cohomology, which also goes by the name of relative twisted cohomology. It is relative in the sense that the hyperplane polynomials BI, which are poles of the physical FRW cohomology, now become boundaries. So the dual cohomology is arranged in a way that it is the direct sum of the twisted cohomology of each cut. And because now we have boundaries to play with, we have residues onto we have residues that we can take. So J is a multi-index that will denote a sequence of residue or equivalently cuts. And M sub J is going to be the topological space associated to the restriction on a given boundary. And this symbol delta is the co-boundary symbol, and it induces a residue operation via the intersection number. And after doing some heavy lifting using intersection theory, we arrive at the first important result of our work, which says that the physical subspace is spanned by all FRW forms that have compatible sequential residues with the physical FRW form. So the task ahead is, given any n-site L-loop graph, we want to organize a basis of forms that have compatible sequential residues with the physical form we start off with. So we go back to our pedagogical three-site example. As we've already seen, there are 6 hyperplane polynomial factors, BIs, giving us the three-dimensional FRW form. This FRW form lives in three-dimensional complex space with the twisted lines and the hyperplane polynomials BIs removed. But from now on, we'll be interested in the space M sub J, where M sub J is the topological space associated to the localization or the restriction onto a particular cut. So the hyperplane arrangements in cosmology are degenerate in the sense that they satisfy linear relations. And for the three-site case, we have a single linear relation given by B2 plus B4 equals B5 plus B6. And the way to get to these linear relations is we simply consider cross tubings, and we simply uncross them on the left-hand side to get to the full linear relation. So one can explicitly check that B2 plus B4, B2 plus B4 definitely equals B5 plus B6. Okay, so that brings us to step 1, which is to classify all non-trivial cohomologies corresponding to each cut. So we first classify all 1 cuts. Now we had 6 hyperplane polynomials onto which we can take residues. And as you can see, I have color-coded them. And M4 is special because of all the 1 cuts, M4 is the only 1 cut that has a bounded chamber, and it is the only 1 cut consequently having a non-trivial cohomology. The remaining 5 1 cuts associated to M1, M2, M3, M5, and M6 have 0 cohomology. So similarly, we can classify all such 2 cuts. There are 15 such 2 cuts, out of which only 8 have non-trivial cohomologies, and there are 16 possible 3 cuts having non-trivial cohomology. So all in all, we have 25 bounded chambers, and naively, we should associate 25 FRW forms for our DEQ basis. But there's a step 2 in which we classify all our non-trivial cut cohomologies in step 1 into physical, unphysical, and degenerate cuts. So physical cuts have non-trivial sequential residues on the FRW form. However, we need to weed out unphysical cuts, and unphysical cuts yield trivial sequential residues on the physical form. So these annihilate the physical form, and these are called Steinman relations and have been studied in the cosmological context by these authors. But one thing to note is that this unphysical sequence always corresponds to a sequence of residues that saturates either side of the linear relation. So 2 and 4 and 5 and 6 are always unphysical residues and give trivial results. However, hyperplane arrangements in cosmology are degenerate. So there are sequences of residues that correspond to the same loci. So the upshot is that we can always pick out 1 physical form from this degenerate subspace. So all in all, we are left with 16 physical forms for the DEQ system. So this 2-step classification lands us on the physical subspace of FRW forms for any n-site L-loop graph in cosmology. And it only needs the knowledge of non-trivial cut cohomologies plus the system of linear relations obeyed by the hyperplane arrangement. So we can systematize this using graphical rules via so-called residue or cut tubings. So in comparison to the solid tubings I showed you earlier, these dashed tubings define an instruction to compute a residue on the hyperplanes involved. So as we will see, the enumeration of all the physical cut tubings correspond to all the different ways to factorize the cosmological graph into products of flat space amplitudes only. So let's go back to the 3-site example. So as we've already seen, there was only one cut that was physical, and this corresponds to the so-called scattering facet of the cosmological polytope. And this gives us the 5-point amplitude, 5-point flat amplitude. And this motivates us to define the so-called unidimensional cohomology condition, in the sense that we cannot have any cut tubings that do not enclose all the vertices of a graph, and we should not have any cross tubings. So moving on to the space of two cuts, we can evolve the scattering facet tubing, which I had in the previous slide, to form all possible two cuts. But however, we need to keep in mind that we cannot have unphysical two boundaries. So that motivates us to define the good cut condition, which eliminates these unphysical two cuts that I was talking about. But however, there are 4 physical two cuts that can be paired with B4, namely B1, B3, B5, and B6. And these are 4 different ways to factor the 5-point amplitude into a product of 4-point amplitude times a 3-point amplitude. There's also the possibility of these following two cuts, which is consistent with the cohomology condition I told you before. Now, we move on to enumerating the space of all 3 cuts. So the first step in doing that is to keep evolving the scattering facet tubing, but now with the extra subtlety that we have a degenerate 3 cut. So as I already spoke about in the direct way of doing things, there are degenerate cuts that one needs to account for as a consequence of linear relations, and this motivates us to define something called the degenerate cut conditions. It takes into account all the degenerate cuts and counts them only once towards the physical basis. Similarly, we evolve the 2 cuts that we had obtained using the rules that I told you before, and we also have the possibility of the following 3 cut. Now, all these 3 cuts decompose the 5-point amplitude that we started off with into its basic building blocks of 3-point amplitudes. And our enumeration ends here, and we've enumerated all the 16 physical forms that contribute to the DEQ system. So these graphical rules, just these 3 rules, the cohomology condition, the good cut, and the degenerate cut conditions, are enough to enumerate the physical subspace of FRW forms for any n-site L loop graph. At tree level, this explains the counting given by kinematic flow. And surprisingly, these cuts get organized in a Pascal triangle structure. We agree with the counting presented for n-gons at 1 loop. And this is quite powerful and allows us to make predictions for the number of physical master integrals, say, for the 2-site L loop graph. This matches with the counting presented for the sunset graph using loop level kinematic flow. So it would be nice to understand why the physical subspace of forms favors only cuts corresponding to products of only flat space amplitudes. And the flow that I showed you for the 3-site case seems to encode the information of how forms talk to each other in the connection matrix. So it would be nice to understand, it would be nice to derive the differential equation or the connection matrix using this flow of cut tubings. And it would be nice to also extend this analysis to more realistic, more phenomenologically relevant theories in cosmology. So, thank you.
Are there any questions?
Yeah, thanks a lot for a beautiful talk. Once you have this connection matrix A, what is, according to your taste, the next step in the workflow? Is it path-ordered exponentials of this connection matrix? And
yes, we want to solve them for in a series expansion in epsilon. That's relevant for inflationary correlators, but we can solve them for a generic epsilon too.
Are there further surprises like dropouts or sparseness properties once you have multiple products of the matrices?
Well, our connection matrix is definitely more sparse than what's in the literature right now. So I think, yeah, it enables for, yeah, I didn't understand the question, sorry.
The question was whether its square is even more sparse than you expect from the matrix itself.
Well, it is as sparse as it can get, and that enables us to integrate it very easily.
Okay, thank you.
Any more questions? No, that's fine. Again,